What up, players? Back from break. This is Unit 7-1, area between two curves. This is Unit 11 in our Calc BC, our Calc AB material. We're going to kind of fly through Unit 7 here. There's a couple of new things. We got to make sure we understand what's going on. Some disk method, some shell method we did not cover in Calc AB. Okay, so Calc section 7.1, area between two curves. I want to find the area region between two curves using integration. All right, pretty easy. So we can extend the idea of definite integrals, finding the area of a region under a curve to the area of a region between two curves. And you probably remember this if you got to Unit 11 last year. If two functions are both continuous on an open interval a to b, so on this closed interval a to b, then the region between the curves can be found by subtracting the area of the upper region and the area of the lower region. So for instance, if I do this, okay, here's my function here. This is the area of the upper region, okay? The area of the upper region is basically saying because this is on top, I want to find all of this area right here, all the way down to the x-axis. Then I'm going to subtract the area of the lower region. So this is the lower function, and we're finding area, right? So it's really underneath the curve, okay, underneath to the x-axis. So I'm going to take the whole function, and I'm going to subtract off this little bitty piece, but you can see that they overlap right underneath that function. And so what happens is when I subtract off that piece, I get what's inside between those two curves. So this is the f of x minus g of x is equal to the integral from a to b. So this is a here, this is b here, it's where they intersect, of the top function, this is the top, minus, then this is the bottom, okay? And then dx. That's all we're basically doing in this section, okay? So here's an example. I want to find the area of the region bounded by the graphs y equals x squared plus 2, that's this parabola, y equals negative x, that's that line, between x equals 0 and x equals 1. So x equals 0 is here, that's terrible, but that's okay, and x equals 1 is right here. But this function actually goes below the x-axis, so we got to make sure we account for that piece. So I'm finding all of the area all in here. Okay, that's what I want to do. So how do I do that? I'm going to make an integral. The integrals are the bounds, so from 0 to 1. In this case, the lines and parabola do not intersect, but it'll tell you what values you want to go between. If it gave you like y equals x and y equals x squared, then these touch at some points, right? They touch at 0, 0, and they touch at 1, 1. And so then you would use between 0 and 1 because that's where they would actually touch. All right, I'm not doing that right now, but that's what you would do. Let's do... There we go. Okay. So I have the integral from 0 to 1 of the top function. Well, the top function is the parabola. We can easily see that. So I'm going to say it's x squared plus 2. Okay. Now, what I would be doing is I'm going to subtract off, right, because it's f of x minus g of x. But g of x is actually the negative x, right? And so hopefully we see that as well, and that's minus, and I want to put all of this in parentheses, and that's dx. If you don't cover that all in parentheses, the grading on the free responses could be marked as wrong. They're pretty lenient, and it might not be, but just don't get in the habit of forgetting the dx there. So now I'm going to kind of make this a little easier to read. So from 0 to 1, this is x squared. This is a plus, right? So plus x plus 2 dx. Now I'm going to integrate it. So this is equal to x to the 3 over 3 plus x squared over 2 plus 2x from 0 to 1. Okay? And you can plug that in and do that math out. And you're going to get basically 17 over 6. Okay? You know how, hopefully you remember how to do that, right? So it's 1/3 minus 1/2 minus 2. I'm sorry, plus 2. Oh, this is plus there. Oof. Minus, and then 0, 0, 0, so minus 0. So this here becomes 17 over 6. All right? That's how you do that one. Let's go to the last one there, and let's call it a day. Oh, we got 2 examples. Sorry. Oops. Oops-a-daisy. This one here, so the 2 graphs are drawn, okay? I want to find the area of the region bounded between this upside down parabola and this straight line. And so it's bounded between, so that means I'm going to use all of this piece here, Okay, and because it doesn't give me the values that I have to use, so I have to find this value and I have to find this value over here. So what I have to do is I have to set them equal to each other. So 2 minus x squared equals x, and I have to solve. All right, I'm going to bring this over and bring that over. So I get x squared plus x minus 2 equals 0. This is going to be x plus 2, x minus 1 equals 0, x equals negative 2 and 1. So these are going to be my bounds. All right, negative 2 and positive 1. So I'm going to say, okay, the integral from negative 2 to 1 of the function. What's the top function? Well, the top function is that parabola, right? So that parabola is 2 minus x squared, right? 2 minus x squared minus the bottom function, which is x, right? So minus x. Again, I'm going to put my double parentheses and put my dx there. Let's clean that up. So from negative 2 to 1, this is going to be negative x squared minus x plus 2, and all of this is dx'd. I'm going to integrate it. Okay, so I get negative x to the 3 over 3 minus x squared over 2 plus 2, and all of this is from negative 2 to 1. All right, you can plug in those values. I'm not going to do that. Again, I'm going to save some time here, but you're going to get about 4.5. Okay, so that is this area right in there. That's about 4.5. Okay, sweet, fantastico. Let's move on. Last example here. So the sine and cosine curves intersect infinitely many times, bounding regions of equal areas, right? So all of these here are all the same. They're all the same areas. Okay? Find the area of each one of these regions. So how do I do that? Well, we know that hopefully I know that the blue curve, okay, this blue one is our cosine graph. And the red one, I think that's red, I don't know, I'm colorblind, is our sine graph, okay? So what I need to do is I need to find out the intersecting point. So let's find out here and here. Let's see if I can find those two values that intersect. So I need to set the functions equal to each other. So sine x is equal to cosine x. And thus, let's see, I get, if I could divide, right, so if I say, okay, I'm going to divide by cosine x here, because we know it's not 0, okay, we know cosine's not 0, so I can do this. This is okay to do. So sine over cosine is tangent, so tangent of x is equal to 1, because this is 1. Well, where is tangent of x equal to 1? Or really, where is sine equals to cosine? Well, sine is equal to cosine on our unit circle here at pi over 4, okay, and at 5/4 pi, which is down here, or 5 pi over 4. Those are the two places that cosine and sine are equal. This is positive, right? Positive pi over 2, or root 2 over 2, and this is negative root 2 over 2, but they're still the same. They're still equal to each other. So we know this is pi over 4, and we know this is 5 pi over 4. Okay, great. Great, great, great. So I'm going to integrate now from pi over 4 to 5 pi over 4. And the top function in this case is sine, right? So sine minus sine of x minus cosine of x. And all of this is dx'd. Okay, cool. I'm going to integrate now because it makes it nice, right? So the integration of sine x is just negative cosine. Minus the integration of cosine is just sine. And then all of this is being evaluated from pi over 4 to 5 pi over 4. All right, and then you can do the math again. Cosine of pi over 4 is root 2 over 2. Sine of 5 pi over 4 is root 2 over 2, and so on. And you're going to end up with, once you do everything kind of nicely, you're going to end up with 2 root 2. Kind of breaks down really nice. Don't put it in decimal form. That's stupid. So 2 root 2 is the value of each one of these areas infinitely all over. So if you wanted to find a bigger bounds, you could definitely do that. But, you know, that's all we needed to know right there. So there we go. That's it for this one. On to the next one. Deuces.